Okay, so I'll discuss two more examples of Taylor polynomials. And the first example is the well-known example of the exponential function. So we take f of x equal to e to the power x. Let us take our base point a equal to 0 and the degree of the polynomial equal to 4, and we know that all derivatives of e to the power x are equal to this function itself. So plugging in, determining the fourth order Taylor polynomial is quite easy. So let us do so. Okay, we wanted to do the fourth order. What do we get? It's equal to the function value at 0 plus the first derivative at 0 multiplied by the difference of x and 0 to the power 1 divided by 1 plus the second order derivative multiplied at the point evaluated at the base point 0 multiplied by x minus the base point to the power 2 divided by 2 factorial. Okay, we have the third order derivative evaluated at the base point 0 multiplied by x minus the base point to the power 3 divided by 3 factorial, and then as the last term the fourth derivative evaluated at the base point 0 multiplied by the difference between x and the base point to the power 4 divided by 4 factorial. Now, since the derivatives are all equal to the function itself, and the function itself evaluated at the point 0 is equal to e to the power 0 is equal to 1, we get 1 plus 1 times x minus 0, so 1 times x, plus 1 times x minus 0 squared is x squared divided by 2 factorial, plus x to the power 3 multiplied by 1 divided by 3 factorial is 6, and the last term is 1, the fourth derivative at 0 equals 1, multiplied by x to the power 4 divided by 4 factorial. And if we write out the factorials, we get 1 plus x squared over 2 plus x to the power 3 divided by 6 plus x to the power 4 divided by 4 factorial is 4 times 6 is 24. So what does it tell us? That if we calculate the value at 1, then we get 1 plus 1 squared plus divided by 2 plus 1 to the power 3 divided by 6 plus 1 divided by 24, and it is something like 2 plus 12 plus 2 is 14, 15 divided by 24, and we can cancel the common terms in the denominator and the numerator of this fraction, which is the common term is 3, so we get 2 plus 5 divided by 8, 2/5, 8/8. And our suggestion was that it is approximately equal to the function value at point 1 is e. So this should be an approximation of the number e, and we know that it is approximately equal to 2.71 something. So we are already quite close to the point e. Another example where the derivatives are a little bit more complicated is when we look at the function f of x equals to the square root of x. So for convenience it's better to calculate the derivatives explicitly, so let us do so with let us do so up to the third derivative. So the first derivative is 1/2 multiplied by x to the power minus 1/2. The second order derivative is, well, minus half goes down, so we get minus 1/4 times x to the power minus 3 over 2, because the power decreases by 1, and the third derivative is equal to, well, what? The power goes down, so we get minus 3 over 2 multiplied by minus 1/4 is plus 3 over 8 multiplied by x to power, which is 1 less than minus 3 over 2, so it is minus 5 over 2. So we now look at the third order Taylor polynomial. So we take n equals to 3, and let us now look at the base point a equals 4. Then we get, what do we get? P3 4x is equal to the function value at 4 plus the first derivative of our function evaluated at base point 4 multiplied by x minus 4 divided by 1 plus the second order derivative evaluated at the point 4 multiplied by x minus 4 squared divided by 2 plus the third order derivative evaluated at the base point 4 multiplied by x minus the base point to the power 3 divided by 3 factorial, and this is equal to what? Well, the square root of 4 is equal to 2. What is the derivative? It's 1/2 multiplied by 4 to the power minus 1/2. So it is 1/2 multiplied by 1 over the square root of 4 is 1 over 2 multiplied by x minus 4. The second derivative at 4 is, well, we get minus 1/4 multiplied by x by 4 to the power minus 3 over 2. And so this is minus 1/4 multiplied by 1 over 4 to the power 3 over 2. So we will write it out in a minute. Multiplied by x minus 4 squared divided by 2 plus the third order derivative at the base point 4, which is 3 over 8 multiplied by 4 to the power minus 5 over 2, so it's 1 divided by 4 to the power 5 over 2 multiplied by x minus 4 to the power 3 divided by 3 factorial 6. And so we can now write out all these terms. So we get 2 plus 1/2 times x minus 4 plus, well, this is, together we have 1 over 8, and 4 to the power 3 over 2 is 4 times square root of 4 is 2, so this is 8 times 8 is minus 1 over 64 plus, what do we have here? 3 in the numerator. We have 4 to the power 2 multiplied by square root of 4 is 2, so we have 16 times 2 is 32 times 84. Now we have to calculate that. So this is already a very small number, and if we would like to approximate the function at the point 5, so square root of 5, then supposedly this is approximately equal to the third order Taylor polynomial with base point 4 evaluated at the point 5, and this is the latter is equal to, well, we have 2 plus 1/2 times 1 minus 1 over 64 times 1 plus 3 over, we can just cancel out common terms, 16, we get 16 times 32, so it's 256, 1 over 512 multiplied by 1 to the power 3, and we can compute this. And this is a number which is very close to 2.5. Now clearly we can compute approximations of the function at a particular point when we start from a base point where the function value has a very simple expression. So that is the idea. However, of course, I can tell you that these values are the function value at 5, so the square root of 5 is approximately equal to this value of the polynomial, of the Taylor polynomial at 5, but how are we guaranteed that this is indeed true? So we need to have some bounds on the difference between the function value and the value of the Taylor polynomial.